Hello everybody. How you folks doing today? Happy Tuesday. Alrighty. Hope you had a good yesterday. We didn't have a lab, given we didn't actually get to a whole lot of stuff last week. So that's okay. Hopefully, I think a lot of you used that time to finish up this current project here. So we're going to pick up search trees today. We had to move them back a little bit and get to really covering the search trees, but that's okay. So we'll get to that, and then we can move into sorting and selection. And we are getting close to wrapping everything up, which is awesome. So we'll talk about the polynomial project today, and then we'll get into binary search trees. And then I think on Thursday we can talk about our sorting and selection, and then we'll be caught back up to where we need to be for that. Okay. And then again, we do have some extra time, 4:15 or so, just final project work time, 4:20. I don't have any lectures planned. I wasn't planning on being live at all. I'll just be around and available to hop on Zoom calls or over Discord if you folks have questions about the project. Okay, So definitely that's going to be the focus as we wrap this up. You'll get more into binary search trees if you take the data structures class or algorithms analysis class. You'll do that again with sorting and selection. So we're just going to touch them kind of at a high level. We're not going to get into too many of the details for them, which should leave us with some extra time, which should be good. I know I had a couple of people concerned that they didn't quite get everything done in the project. There's definitely partial points, right, based on what you had here. So definitely you can get points even if you didn't finish it all. And then what I'll typically do is I'll take your score on the final project and I'll use that score to replace any individual project that you didn't do so well on. So if you do better on the final project than one of the individuals, I'll just replace that percentage score and you can take those points instead. You know, if you do the final, that's really the big concern of mine. And you know, that's okay. Things were happening, and life is hard, and we're still in remote learning nonsense. So we'll just go from here. All right. So I've got a new project up and ready to go here for project 3. So we're going to write our polynomial project. All right. So the first thing we're going to do is we're going to add that term node inner class here. All right, and an inner term node then needs a coefficient, an exponent, and a next. Right, and I'm going to say next is none if you don't tell me otherwise. Coefficient, did I spell that wrong? I'm so glad it can spell check things for me. What was it doing? Spell checking it, right? No. Rename typo. Coefficient. Is there 2 F's? Ah, 2 F's. Okay, sure. Okay, and I'll take a self coefficient equals that coefficient, and then the self exponent equals the exponent, and a self next equals next. So it sets up our term node. Yeah, missing that. So my laptop has been running hot lately, and then it throttles the CPU when it gets too hot. So I've got a second laptop set up here that I've got the stream monitor on where I can watch chat and everything. So if you see me going like this back and forth, I'm trying to find you folks over on chat instead of going up and down. So, all right, so we've got that. And then here, let me throw this up on my other screen here, make it a little easier. And then we needed to be able to figure out whether or not we were equal to another. And the idea that we are equal, one term is equal to another term, is if first we want to check that the type of other is type of self, right? That we're the same type, right? And really we can just return this here. Because if that's not true, then we're done, right? The whole thing's false. We'll say that and self dot coefficient is equal to the other dot coefficient, right? And I'll just bump these down a line here, right? And we'll go and oops, self.exponent is equal to the other dot exponent. Right? If we match, why is that not hanging right? Okay. So we're equal. So if we have the same coefficient, same exponent, we're going to say we're the equivalent term. We're just going to ignore next for this purpose. Right? It is one term at a time, you know, to be able to compare that. And then not equals, nope, not neg, not equals, nope, wrong one, not equals. There we go. We're just going to return not self equal other. Right? We already did the work, so just do the opposite of that. Okay? That's our term node. That's our internal storage for individual terms in a polynomial. Okay? Then we're going to define the init method here for polynomial. It needs a coefficient and an exponent. I'll just copy paste. Right, so this is the initial polynomial coefficient and exponent. So we're going to have a self, our first node, or the first term or head, whatever you wanted to call it here, was self.term node, given the coefficient and the exponent. This equals and not equals is so that we can compare terms. So we're going to say, hey, if my terms are equal, then my polynomials must be equal. Because the polynomial itself needs to have an equal and not equal to say, hey, does this polynomial, is it equivalent to another polynomial? So we're going to set up our first term as a term node with no next, right? So we always start as monomials. We're just single term polynomials, right? Monomials. It's okay. We'll just take our coefficient and our exponent and we'll store those. Okay? That's all we need to do with init. And that's the only thing it does. It sets up the first term. That's it. We don't have any other variables. Then what we're going to do is we're going to start adding in other functions, right? We need to add, we need to multiply, we need to differentiate, we need to integrate, we need a string, we need an equal and a not equal. We got a lot of functions we need to add here, but we'll work on them. So the idea with add, myself and another, so if we add two polynomials together, we're going to get back a new polynomial result. So we don't want to change ourselves, we don't want to change the other one. We're going to get back a new result. So we need to take all of my terms and all of their terms and smush them into a new polynomial, right? So I'm going to take mine to start. So we'll make a new polynomial. I'll just call it new poly for now, equals a polynomial given. And now I'm going to give it my first term's values. I don't want to give it a term, the term itself. I don't want to have references there, but I want my first term coefficient and the self.first term exponent. So now new poly has the same term as me for the initial term. They should be equivalent terms. We made copies here. We didn't say, hey, the terms both point at the same location. We don't want shallow copies. So we're taking the coefficient and the exponent and saving them here. So now we have a new polynomial. Then I need to check all of my terms and all of the others' terms and start adding them to this new polynomial. So my current term is going to be self.firstNode next. Because I already did my first one. I already did my first node, so I need the next. And then I need the other current term is going to be the other.firstNode. Because we started their first node. I didn't take their first values, I took my first values. And then the new polynomial, I need their term. So my new poly current term is the new poly first node. Is this idea here that where these terms always have a next. They're these singly linked objects where each term will point to the next term and point to the next term and point to the next term. This way I can reference all of those terms. Okay? So if we add them together, right, we started with mine, and then I move to my next. I started at others first node, and then I have the first node of the the new polynomial. And we can start adding them in. Okay? But what we need to do, we need to be careful. When we add the terms, we need to be looking for combining exponents, or combining coefficients if the exponents are the same, and putting them in the correct order. I didn't even check to see which one was bigger. Right? I'm going to do that in a minute. Okay? So what I'm going to do is I'm going to add a helper method here, the little private method here. Let's say add term in descending order, given self and a term. And we'll call it, yeah, we'll just call it a term. See, if you want to add a term in descending order to self, we can do that. Right? Given a polynomial, we'll add a term and make sure it's in the correct order. So this is where the meat of this is going to happen. I'll figure out how that works in a minute. So what we can do then, we can just say, while current term is not none, we're going to take new poly, right? And we're going to call add term in descending order, given the current term, and then my current term is current term next. So because this works with terms, right, I'm just going to be able to add it to the polynomial. This is a helper method in the polynomial class. So I don't even need its new term, right? I'm going to work with that individually in this helper method. I'm going to take the big problem and break it down into smaller problems. We'll figure out how to do that after, okay? And I do the same thing. I say, well, other current term is not none. Right? I'm going to take my new poly. I'm going to add term in descending order, the other current term. And then other current term equals the other current term dot next, right? Move to its next. So we're going to add all of mine. We're going to add all of theirs. Then the magic is going to happen in here, right? This is an easier problem to solve one term at a time. How do I add a term in descending order than to figure out, hey, how do I put them in the right order? Either way works. Some people took the approach, they would see which one was bigger. They would loop through both, taking the biggest one. Right? We could do that. And I think that's what I showed when I kind of demonstrated how that would work, right? We could take the biggest of each. I think this is actually easier than doing that. I'm just going to take all of them and put them in the correct order. Okay? So we need to check. So the first term should be the largest exponent. So we need to check. We're going to see if term.exponent is greater than first node dot exponent. If it is, then I need a new first term. Right? So what I'm going to do is I'm going to take the term.next and I'm going to set it to self.first node. So you must come after. If you're bigger, I have to come after you. So I'm going to put your next as my first node, and I'm going to change my first node to be the term. Right? So now I point to that first term. Right? Else if my term exponent is the same as my first term, first node exponent. If they're the same, well, I just need to add the coefficients together. So my first node dot coefficient is plus equals the term dot coefficient. We'll add the coefficients together. If they're not the same, if it's smaller, well, I need to see where is it going to go. Right? And at this point, I'm going to find out, does it go, where in between does it go? Because if it didn't go before my first or merge with my first term, it's going to come after or between the next set of terms. Okay? So if it's not the first, I'm going to have a current term is self.first node. Okay? And then I'm going to loop. I'm going to say while my current term.next is not none. I want to keep on going because I want to keep on looking. If I have a next one, 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 I can keep on going. As soon as I don't have a next one, it's got to go there, assuming it's smaller. Right? So we know the first time it's smaller, for sure. If it's smaller than my next, I need to walk. So we're going to say if term.exponent is less than current term.next.exponent, I need to walk. So current term equals current term.next, right? Move to the next one, right? You folks with me so far? As soon as we're done, we know where to put it. Right? Once this loop is done, if it's not less than, right, then I need to put it there. So my else, or if it's equal, I guess, right? Else if my term.exponent is equal to the next exponent. Because I'm always working with the next value here, because I know it's not the first. So if it equals the next one, then current term.next.exponent, coefficient plus equals the term.coefficient. And then our loop can be done. We can break. Break is a little ugly, but it's you'll get the job. Or we just return. There we go. We just return. We're done. There we go. That method's done. Okay. If we're not less than and we're not equal to, we must be greater. Well, we need to go in between, right? If we're not less than the next, we're not equal to the next, we must be greater than the next. So then the else case is we need to go in between. We'll take the term.next, we'll set it to the current term's next here. And then the current term's next is going to be me. And we're going to put ourselves into the mix here. Right, so if we kind of draw that out, sketch that out here, let me let my whiteboard load in a second. All right, whiteboard, come on. Clear. Let's see if that'll go here. Oh man, it's getting hot in my office. Oof. That's crazy. I had the window open. It was really nice earlier, and now it's just getting really hot. I gotta print this real quick. Sorry. This might be a little noisy on the printer. Black. See if it'll wake up. Oh, I'm running low on blanking. Bummer. Okay. So if we had some terms like 7x to the fourth plus 3x to the second, and we're going to add in another term. We're going to say, how about 3x to the third? Okay. I'm going to take all of my terms and I'm going to throw them into the new polynomial. So I have 7x to the fourth. Its next is going to be 3x squared. We just keep on adding it in. right? Well, actually, we can build it all up from scratch, right? We'll say, okay, it doesn't have a next currently. We're going to go add a new term. So it's not equal to, but I don't have a none. So what am I going to do? Well, this new term's next is my current term's next, which might be none, right? If it is none, that's fine. No big deal. Right? And then the current term's next becomes my term. So I'm not greater than, I'm not equal to, so I'm going to start with the current term being the head here. So this is my current term. Current term. Okay? And then I'm going to say, hey, while the next is not none, well, its next is none immediately. So sure, this one happens. So as soon as it's greater than, right, we're going to be done. Hey, we could even put that in the loop, right? If the next is not none and term.exponent is greater than, no, we want that to be less than or equal to current term's next exponent. There we go. Look at that. So it's either less than or it's equal to. Right? We know it's got to be. So this could just be an else. Look at that. Oops, I didn't want to delete all that. Sorry. There we go. Okay. If they're equal, great. If they're less than, keep on going. If they're less than, keep on going. As soon as they're equal, great, add it. And as soon as our loop is done, then if we haven't returned, right, we know the next one can be current next, right? The new term's next is the current's next because it's either none, which is fine, or it's less than, right? Or it's not less than, it means it's greater than. If it's greater than, the loop doesn't run, and we need to go in between. Let's see, why did that not like my printer? It's supposed to print. Come on, friends. Don't want it offline. Pause. Pause. Make it go online, silly. Can you just wake up? It's all plugged in. That's weird. Come on, printer. All right, so this should add terms for us then, right? In descending order. This is where the magic of that happens. So I don't want to have to deal with which one goes where. I just want to do one term at a time. So kind of break that problem down into a smaller problem. And I can just add them in descending order as we go. When I'm done with that, I'm going to return the new poly. Right, here's my new polynomial result. Come on, printer, wake up. Will it restart? Okay, it found it. It's a good sign, maybe. Cancel all jobs. Skip that. Come on, why is the printer offline? Use printer offline, use printer. All right, I was thinking about it. It's 2021, this should not be so hard. There it goes, it's sent to printer? Maybe? Printer is dumb. No, nothing. Printer. This printer is not working. All right. Sorry. Really should just go. Let's see. Can we remove? We'll add that one. Failed to add. That's nice. Why is this so hard in 2021? It wasn't listed. discoverable printer. All right, so we should be able to see now if add works here. But we don't have a way to toString these yet, so we want to figure out how we can add these to string. So we're going to define the string representation of ourself. Now, right, this idea, we want a something x to the power. Right, so we're going to keep on going. So we're going to have some result is empty, and then we're going to say my current term is self.first term, first node, and while the current term is not none, I want to keep on adding these. And we're going to fix these up later. We're just going to make it a little bit ugly to start, and then we can come and clean them up here. I'm going to say my result plus equals, I need the coefficient, current term, coefficient, plus an x to the, plus the current term, dot exponent. Okay, so we're going to string all this together, plus a space, and another plus sign, probably in another space, right, to try and clean that up. And when we're done, we'll return the result. But actually, I don't want the last 3 characters. So I'm going to return that -3. Right, that should remove the last 3 characters. So we can see if we can string some of these out. So I'm going to add some tests right away. See if we can add some tests. Polynomial. We'll go to test. Create some tests for polynomial. Sure. I don't need to test that one. Okay. Fine. Test toString. I don't know. Test string. We're going to arrange. We'll act. And we will assert. So the first thing then, I should have an expected string is, we'll say like 3x to the 7th. So let's make a polynomial. So we'll have a poly equals a polynomial. Oops, from, we should rename this here. We'll, rename. We'll call this polynomial. From polynomial, import polynomial. Okay. Polynomial, say 3 and 7. Coefficient and exponent. And then we'll have an actual string. String version of poly. Right, and we can assert that they match. So self.assert equal my expected string and my actual string. Let's give that a run. See what we get. No network printer found. Why do my printers hate me? It showed up on the list a minute ago. Maybe I'll turn it off and back on. Here we go. Oh dear, it failed. Uh-oh. Unsupported operand types for string and integer. We need to turn these into strings when we toString them. Go figure. So I want a string of the coefficient plus a string of the exponent. Okay, we'll go back and run our test. It's thinking hard about it. Oh, bummer. I forgot here. I never, I'm just appending to result forever. Current term needs to walk, right? Current term.next. Right? We need to make sure we're moving this to the next one. Otherwise, we've got an infinite loop there. And we'll try our tests. And look at that, it worked. We got what we expected. Okay, looking good so far. Now let's see if we can add. So we'll define test add here. So again, we need to have some expected strings, some actual strings. So I'm going to make 2 polys. So poly1 equals maybe 3x to the 7th. And how about poly2 is a polynomial? What about, I don't know, 5x to the 3rd here. Okay, and then let's add them together. So I'll have in poly3 equals poly1 plus poly2. And then the actual string is string of poly3. So that should be 3x to the 7th plus 5x to the 3rd. Right, if we did that right. Okay, let's give that one a run. Okay, that seemed to work. Now I want to try in both directions actually. I want to have actual string 1, and I'll have another version here. I'm going to say poly3 is equal to, let's go 4, it doesn't matter, poly2 plus poly1. Let's do it in reverse order. I'll have an actual string 2, string of poly4, string here. Sorry, some of these variable names are terrible, but I'm not feeling too bad about it yet. That's okay. 2. So we'll try both ways. We should get the same result no matter if we add the one to the other or the other to the first. Uh-oh. Term node has object has no attribute coefficient. I misspelled coefficient here. Coefficient. Man. Did I? No? Must not have misspelled it. Did I misspell it? I probably misspelled it. Yeah. I don't know how to spell coefficient. There's an extra letter in there. See, this is good. I'm picking up some errors. And it only showed up because we did a smaller one. Oh dear. The bigger one. Uh-oh. All right, we expected 3x to the 7th. We got 10x to the 3rd. I think we added something we probably shouldn't have added. Let's see. So how would we have done that? If the exponents are the same, we would have added. Current term is not none. Keep adding. Current term is next. Others next. Huh. That's really interesting. So it was only in this case when I added 2 to 1 that it happened. So I'm going to put it in debug mode, and let's see what we did. Let's debug our test. We'll step into. Okay, so we're going to step in. So now we've got 5x to the 3rd and 3x to the 7th. So the first term in new poly should be 5x to the 3rd. So let's step. My new poly here is 5x to the 3rd. Looking good so far. Current term is none. So we shouldn't add any more. Cool. Good there. Other now. Other current term. 3x to the 7th. All right, we're going to add that other current term here in order. So let's step here. So self is 5x to the 3rd, and we're adding another term, which is 3x to the 7th. So the term exponent is greater than my first node's exponent. So we're going to say, okay, so the terms next needs to be the first, and then my first becomes that new term. Aha, I did a bad thing. Did a bad thing. So when I did this here, right, this term that was passed is not a copy. That's the problem. That's bad news. We want a copy of that term. So I want to make term equal a new self-term node, given term.coefficient and term.exponent. This way I'm going to have a copy of it, or I could just use the deep copy. This ought to do it. So I had a copy here. When I set its next to that one, when I came back, now all of a sudden other current term had a next, which was me. We did a bad thing. Let's try that. All right, that looks a little happier now. Okay, let's see, did my printer come back now? I didn't turn back on. All right, that was a good catch, right? We found that. So now let's see, can we add one with, this is add monomials, right? Sure. Let's add polynomials. Oops, that's too far in. There we go. So we'll have poly3 is that one. And then we want to add another term to it here. So let's add, say, poly4 is, how about a polynomial given, let's see if we can get one that is, I'm going to do with duplicate exponents. How we do like 3 to the 3rd here. So we should get then 8x to the 3rd when we're done. Right, so it should be poly3 plus poly4. Here's my actual string, poly4 You know, and maybe we want to test in both directions again. I like that idea. Testing in both directions, I think, is a fine idea here. Poly 3 and poly 4. This will be what? Poly 5 is 3 and 4. And 6. Oh my goodness. These are terrible names. I'm sorry. It's 4 and 3. So either direction we add it should work if we did this one right. Okay, with duplicate exponents seems to work. It's a good sign. Okay, let's do some more. So now let's do not duplicate exponents. Just add polynomials. Right, so we'll have 3x to the 7th plus 5x to the 6th plus 2x to the 5th plus 3x to the 4th. How about that? We'll add a bunch of these together here. So we'll add those ones, we'll get a result, and then we'll add a 5x to the 6th. And really, we don't need to make them every time here now, right? We can kind of add them as we go, but it's fun to add polynomials together. So we'll have poly 5, the polynomial. We did that one. We need 2x to the 5th, 2 to the 5th. And poly 6 is going to be poly 4 plus poly 5. And then we need, oh, we don't need 8x to the 3rd, we need 5x to the 3rd. We need a 3x to the 4th. So poly 7 is poly 6 plus a polynomial of, how about 3x to the 4th? And then a poly 8, sure, is going to be poly 7 plus poly 3. Right, so we're just going to kind of mix and match here. That's fine. It's all good. And my actual string then should be check poly 8. If we got one that worked along the way, should be good to go. Try that. Just adding a bunch in here. All right, that seems to work. So far we haven't handled a negative case yet, though. Right, and that's really testing out our toString here. So what we want to do when we're toStringing is if we get a negative value, I don't want to add this plus. Right? So we'll check. So before we add that, then we can check here. No, I don't even want that. We'll say if current term here we go. So we'll just take that out. Okay, before we do that then, we put that back. So before we add it, we can check if my current term dot coefficient is less than 0, right? We need to do something. We want to not have the plus sign in there. I want to just be my negative, and it should touch. So I'm going to take out 2 characters. Result equals result minus 2 characters. Should take that one out. If it's negative, else if my current term coefficient is 0, I just want to skip it, right? We just do nothing. No, so really, okay, so if it's less than 0, how about if it's greater than 0, we add in the result. Okay. All right, how about if it's not 0? We'll add in the result. And then we'll walk to the next one. So if it's negative, strip out the plus sign. And if as long as it's not 0, let's add it in. Keep on walking to the next one. We should be able to get a negative 1 in here then. And it should work. Oh, shoot, it's not going to work if the first term is negative. Will it? And how about we'll do and length of result is greater than 2. Okay, because if we're empty, if we have no result yet, there's nothing to strip out. Okay, we're just going to add it right in. So let's try that. I think that would have failed right away, but that's fine. How about a negative 3x to the 7th? Should be negative 3x to the 7th. That string negative. Oh, it failed. Oh, we can't. Less than is not supported between string and int. Oh, that's a length of result. I have my parenthesis on the wrong side there. All right, let's go back and run that test. All right, so that one worked. So let's do a negative plus a negative, right? We'll have two negatives. Negative plus negative. Right, so if we have that one, and how about, and it's in descending exponential order, so that's fine. So how about negative 2x to the 7th? Oh, really we want like a minus sign there though, right? So we need an extra space. So I don't want to take out both, do I? Well, and we'll just add in a space after. We can cheat. Okay, so we do that one. And then we have poly 2. Oh, here, we'll just do polynomial this plus polynomial of, how about negative 2 to the 7th? Oh, not to the 7th. No, we don't want those to combine. What to the 5th? To the 5th. All right, we expected negative, my expected string. My actual string. Am I backwards? I'm backwards, aren't I? It didn't match. So one is touching, and it shouldn't be touching. So not expected. Am I backwards with the actual and the expected? Oh, no, the actual is touching. Okay, the actual is touching. So it didn't add in the padding back. Shouldn't have added the padding. If we take two characters off, it would have been the plus and the space. Oh, okay. No, so this is... We can't get that because the negative sign is right there. We just need to get rid of that space. That's fine. It's just going to touch. I don't think there's anything we can do about that. Because the negative 2 is the coefficient. It comes right out there. That's all. That's okay. Sure. We'll call that good enough. All right, so we did add. Right, we did string. We're able to add in descending order. We did our add method. Now we need our multiply. Right, so we're going to define multiply, self and other. Okay, so we're going to do the same thing. So we're going to have a new polynomial. It equals a polynomial. Given, well, what? It's my self.firstNode.coefficient times the other dot firstNode.coefficient. Right, that should be the coefficient. We multiply the coefficients, and then we add the exponents. Right, so then we're going to add the exponents here. Let's break that down, bring that down a little bit. It gets really big here. So self.firstNode.exponent plus the other .firstNode.exponent. Right, that's the first term. Okay, that's my first term. Then I'm going to go through and multiply the rest. So I'm going to have a current term is the next, and the other is the other's first. I need to take my first term multiplied by every one of their first terms. Then I need to go back to my next term multiplied by every one of their next terms. Right, so I need a loop inside of a loop. So my current term is not actually the next one here. Right, because I did the first times the first. Now I need my first times their next one. First node's next. And we're going to loop while other current term is not none. We're going to keep on going. Right, we'll keep on multiplying these together. So we'll take my first term times their current term, but I did the first one already. Let's try that. I'm going to start with the next one. What did I do? I had something different here. I had a different idea. Give me just a second, sorry. Find what that was. There we go. Did my printer come back yet? All right, 1 second. All right, so I gotta go take a break real fast. I'll be right back. I gotta go start that music lesson. Alright gang, sorry about that. I'm back. Got that piano lesson going, I hope. It's one of those days. Alright, and then we're working on multiply, right? Because we want to multiply every one of mine with every one of theirs. That's what that's what we want to do. So I don't actually want to do this one here. I'm sorry. I got ahead of myself here. I'm going to have a new poly equals none to start. And then I'm going to start with my first node and their first node. There we go. then I'm going to loop, right? So for every one of my nodes, I want to loop through every one of their nodes. So we'll say while current term is not none, start at theirs, and while theirs is not none, we can keep on going. And this is kind of this a nested loop. Okay, now we're going to check. So if new poly is none, then I need a new polynomial. New poly equals this thing here. Okay, and I don't want that. I need my current term. There we go. Current term, and other current term, and other current term. Oops, that didn't copy paste well. Coefficient. What did I do there? I think I dragged something. So my coefficient times their coefficient, and their exponent plus my exponent is the new polynomial if it's null. If it's not none, right, then I'm going to take my new poly, and I'm going to add, come on, in descending order, a new term. Self.term node, and I need these values here for the term node. Right, so add a new term node with the coefficients multiplied and the exponents added. It gets a little messy there. It's all right. Okay, and that's going to do that for every term as long as theirs is not none. So we need to walk. So my term equals the term.next. When that's done, when other current term is none, this loop is done, and now current term needs to walk at the end of that. Current term next. So this goes to my next term. When that loop is done, then I can return the new poly. So this should multiply every one of my terms times every one of their terms. New poly. And it's just using a little, if I haven't created the new polynomial yet, here's the first term, otherwise do this here. That's our little, makes life a little easier for us. Okay, so that should be able to multiply. So we're going to try some multiplication. Let's try some tests. So test multiply. So we're going to arrange, we'll act, and we'll assert. So if we're multiplying expected strings, if we're multiplying monomials together, right, like 6x to the 7th would be, so poly 1 is a polynomial, would be, what, 2x to the 3rd, and poly 2 is polynomial of, say, 3x to the 4th. Oops, sorry, we don't need those, just commas. Okay, and then we'll multiply them together. So poly 3, poly 1 times poly 2. And then my actual string is a string version of poly 3. We can assert those are equal. So assert equal my expected string and my actual string. Oh dear. We expected 6x to the 7th. We actually got 6 comma 7. Well, that's not quite right. String of poly 3. Oh, we didn't. Did we return? We did return the new poly. Oh, that's right. I just made a tuple there. This needs to be a polynomial. There we go. Make it a type of polynomial. That ought to work a little better. There. Okay, so the single multiplication worked. We added those ones together. Let's try some longer ones here. Right? Let's try get a couple of these here. Multiply polynomials. This was multiply monomials, right? Monomials. Okay, so we'll make 2 polynomials first. So let's add a bunch together here. So we'll have poly 1 plus, so it'll be 3x to the 7th plus 5x to the 3rd. And then we'll have it poly 2 is a polynomial. Let's give it some other values. How about like 4 and to the 6th plus a polynomial of, yeah, sure, 3 to the 3rd. Okay, so 3 to the 7th times 4 to the 6th. We should get 12 to the 13th. And then 3 to the 7th times 3 to the 3rd, we should get 9 to the 6th. Plus, now 5 to the 3rd times 4 to the 6th should be 20x to the 9th. Plus, and 3 times 3 should be 9x to the 10th. But now those are out of order, right? So 10th should go first, so 9x to the 10th. Plus that one, 20x to the 9th. So it should be in descending order. That ought to work there. We'll try it. And we'll just try it both directions, right? That'll be fun. So poly 5 is poly 1 times poly 2. I guess we should have tried this one both directions as well. Poly 4, poly 2 times poly 1. I like that. String 1, call that 4, and actual string 2, poly 4. Insert. Okay. Make sure those are good both directions. String. Okay, that one was good, so we'll try this one both directions. So poly 2 times poly 1 should work. We'll find out. Uh-oh. 12x to the 13th. Okay, 9x to the 10th. Okay, 20x to the 9th. Yep, 15x to the 6th. Did I do some math wrong here? Or am I wrong? Yep, 5 times 3. That should be 15. 15, not 9. Right, if we actually FOIL that one out, I think we did the math wrong there. All right, how's that feeling? Should we try a longer one? I mean, these were even sized. I mean, we can check some other, but in terms of code coverage, as long as we get into the else, I think we're in good shape in terms of making sure that code ran. This one we wanted a greater than, this one we wanted an equal to, and this one we wanted a less than to make sure this was working. Right? To make sure that, yes, we're going to combine coefficients, and yes, we're going to keep on moving to the other ones here. So we want to make sure all the code is running. Okay? Then we can check a equals. So we're going to define an equals. So first we can check if type of other is not type of self. We can return false right away. Oops, capital F false. Right off the bat. If we're not the same type, we're not equal. Otherwise, we're going to say we'll say current term equals self.first node, and then the other current term equals other.first node. Okay, and we're going to keep on looping. We're going to say while current term is not none and other current term is not none. As long as we're both not none, we can compare. We can check if current term does not equal the other current term, return false. Right? If our terms don't match, they're false. Otherwise, we'll just walk. Current term equals current term next, and other current term equals the other current term dot next. Right? Walk them both. Because they must have been the same. We didn't return, so they must be the same. Keep on going. When that's all done, if we haven't returned false, now we need to check. We're going to return that current term is none, and the other current term is none. Right? Because we should both be none by the end of this. If one of our two terms isn't none, it means we still had more terms. So like the first term's going to match, the second term's going to match, the third term's going to match, and then maybe I had a fourth term that this one didn't have. Well, they were both not none, so it stopped. So we need to check, are they both none? After we've done all of that. And we can just return, if they're both none, true, we must be equal. Define a not equal. We're going to return not self equal other. Okay? So let's go test it. So we're going to define test equals. So let's make two polynomials. So poly 1 equals a polynomial of 3 to the 4th and a poly 2 polynomial of 4 to the 5th. You know what, why don't we add a couple here together? So 3 to the 4th plus polynomial of 4 to the 5th, and 4 to the 5th plus a polynomial of 3 to the 4th. We can assert true. Poly 1 equals poly 2. poly2. And we can assert, self.assert true, and self.assert false. Self.assert false, that poly1 does not equal poly2. Poly1. So like this is the arranged, there's no real acting because this result is right there. Right, and now we're passed. So the twos appear to be equal. Okay, and we want to make sure that we're also checking then that if they just equal different length, we can say they don't equal there if I add another polynomial. Say, I don't know, 2x squared. They should not be equal is true, and equals should be false. Okay, but different lengths, that seems to be good so far. All right, so do we get them all? Let's see. Let's see if we got them all here. Oh, we didn't get differentiate and integrate, sorry. We'll go back to differentiate and integrate. Differentiate. We need a new poly equals a polynomial. And what's the first term? Well, it's the self.firstNode.coefficient. And when we differentiate, we're multiplying this by the exponent. Self.firstNode.exponent. Right, coefficient goes up, and then exponent goes down by 1. So then self.firstNode.exponent minus 1. Right, that's our first term. Right, is that right? We multiply and then subtract? I really should go look, because I'm confused now. So when you differentiate, yeah, multiply and then go down by 1. Multiply down by 1. Okay, perfect. And we're going to say our current term equals the self.firstNode.next. And while current term is not none, we're going to keep making new terms. Right, so we're going to take new poly, and we're going to add a term in descending order. Well, a new term. I need a new self.termNode. Okay, so calling termNode here would be good for that constructor, because we also do it here just in case I forgot. So I don't have to do it. I can just hand it the term. Look at that. That is awesome. But, oh, I need to change the values, though, so never mind. So make a new term of current term dot coefficient times current term dot exponent and current term dot exponent minus 1. Okay, and we just keep on going. So then current term equals current term's dot next. And keep on adding, keep on adding, keep on adding. When we're done, we return the new poly. All right, so let's test differentiate. Test differentiate. So let's make a polynomial and we'll differentiate it. We'll have an expected string, should be what we want. So it'll be 12x to the third plus, oh no, that's backwards here, right? So that should be 20x to the fourth plus 12x to the third. Oh goodness. Oh, that button. It's one of those days. All right, so we'll create a polynomial, and then we'll have a poly2 equals poly1 dot differentiate, and then an actual string is poly2 string of poly2, and we're going to self dot assert equal my expected string and my actual string. And then one other good thing to check here for fun. So we have an expected original would be 4x to the fifth plus 3x to the fourth, to make sure we didn't change the other one. Right? Original string. Right, make sure the poly1 didn't change. Right? We want to make sure we get the new result and the original didn't change. So it's kind of good. Hey, make sure it didn't change out from underneath us here. Okay? Oh. All right, we got differentiate, and integrate is very similar here, but we just do it in reverse. So it's integrate. So it's the other way around. So we take the coefficient divided by the exponent plus 1 in parentheses, right? And then we add 1. Exponent plus 1 divided by that plus 1. Right? We just reverse it. We're going to test integration. Integration. Okay, I'm going to, just for fun, here, let's, we can do them both at once, right? Because if we differentiate and then we integrate, it should put us back to where we were. Let's try that. And then we'll have a poly3 is a poly2 dot integrate. And an integrated string is a string of poly3. And then poly3 should match the original, the integrated string. Let's give that a shot. Uh-oh. 4x to the 5th plus 3x to the 4th is not... Oh, we added in some decimal places. We forgot to do our formatting. Oh, that's going to break all of our tests. Bummer. Okay, that's all right. Remember, we wanted to add in our formatting here to format our coefficients to 2 decimal places. Right? We want to do that to two decimal places. Okay, that's all right. We can break all of our tests. It's no big deal. So if we want to do that, we can do a string format. Right? We do our cool little formatted string. Then our f string. And take the current term coefficient colon 0.02. Oh, and then we don't even need the rest of this too. Look at that. X to the current term exponent. See if that works. Right, doing our little formatted string. We did this back in the first semester. We played a lot with these formatted strings to get some prettier looking output. So now all of our tests should fail. Yep, because they all now want 2 decimal places. 3.0, 5.0. You know what? Let's do this. Let's go here, and I'm going to do a find and replace. I'm going to find, nope, a find and replace. That was the wrong, didn't want hierarchy. Close that. Do a find, and we want to, nope, edit. Where's my replace? Oh my goodness. Find, okay, there's replace. Control R. So we're going to find x to the something, and we're going to replace that with 0.00 x to the something. Right, so we'll replace the first one, the next one, the next one. That one we already did, so I can skip, replace, 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 next, next. Oh, that's the wrong direction. Replace. That one's good. Those are good. Good. All right, I think we got them all. Run our unit tests. Oh. Oh goodness. Precision not allowed in integer format specifier. Why is it an integer format specifier? We broke it. Polynomial. It's not an integer. You know what? I'm just going to Google this, and I'm sure we can find something that will tell us what I did wrong here. Look at that. I love it. I have to have one of the inputs as a float. Convert it to a float? I don't want to convert it to a float. I just want it to be a float. That is obnoxious. That is obnoxious. Well, okay, so we can just say float of the current term coefficient. Now we'll run our tests. I guess we can convert to float. Oh dear, it's close. 0.02? Did I not get the right number of decimal places? Colon point. There we go, colon 0.2. Is that it? Man, I have not done those number formattings in a while. And it shows. Nope. We're close. We're close. 0.3? Well, let's try that and see. Nope. Still not changing the actual. 0.02. Right? Colon 0.02. Colon 0.2. That ought to do it. Oh, we didn't want to run Polynomial. We wanted to run the tests. No. Expected and actual. All right, it is not giving us what we expected. Let's round it to 2 decimal places. I need to do this. Like one more set of parentheses, maybe? No, still. So did that. Okay. Let's just Google it. So Python format. Oh my goodness. Python format string rounding. We're not getting the binary search trees today, unfortunately. Yeah, here. Dot precision. Ooh, I put an F at the end. Is that it? Is that all I needed to do? Let's try that. Let's run those tests. That was it. Oh my goodness, I tell it it's a float there at the end. That's what it is. And then it formats it as a float. Look how beautiful it is. So beautiful. All right, and our tests are passing. We integrated, we differentiated. Let's grab this down here. Make sure we have everything. Right, the term node, we can add, we can multiply, we can differentiate, we can iterate, we turn it into a string, we have equals and not equals. Is that it? Oh, and anything x to the 0. Okay, we didn't clean up anything x to the 0. So if the exponent is 0, well, then we don't want to add the x, right? Okay, so if current term dot exponent is equal to 0, or really not equal to 0, we'll take this one here. And then else, we're just going to take result plus equals just the coefficient, right? Plus, like that, because there's no exponent, there's no x at that point, right? Because x to the something, anything to the 0 becomes 1. We can just get the coefficient. All right, we'll add one more test there for that. We're going to add a define test 0 exponent string. So we'll have an expected string equals, I don't know, like 3.00. And a poly1 equals a polynomial of 3 to the 0. And an actual string of, string of poly1 self.assert equal my expected string and my actual string. And we'll run that test. All right, look at that. So 3. Looking good so far. How do you folks feel about this one? There's a lot to it. It seems a little deceptively simple, but a lot of little pieces here. Again, I liked this idea of trying to break out this add terms in descending order, because that way I don't need to redo any of the work in multiply to figure out which is bigger or smaller. The other thing you could do, you could create monomials and use add if add already knew how to do that. Right, so instead of adding terms in descending order, you just make a new poly and say new poly equals a new poly of this one. And you just make a new polynomial every single time. So we got different approaches. All right, well, sorry we did not end up getting a chance to look at binary search trees. We'll do that on Thursday. We'll get caught up. We got a little bit of buffer time in there, so don't worry too much. Okay? And what can we go do? Let's go pester boring math professor. He's lots of fun. He's not so boring. Okay, so we'll go over that way. Have some fun with boring math professor. Learn some things. Tell me he said hi. And I'll see you folks on Thursday then. All right. Take care, everybody. See you around. And I'll put this out on GitHub for you. Okay? All right. Take care.